So a nice thing about the curvature perturbation as a way of keeping track of the evolution of cosmological fluctuations is that we know its value. We predict from inflation its value when it crosses outside the horizon. And then in most simple cosmological scenarios, it just remains constant during all this time before it re-enters the horizon. And at that point, then things start evolving according to, say, Newtonian perturbation theory. Or, well, you can use the relativistic cosmological perturbation theory to get more accurate results. And so that means that you know at a certain moment in time what its value is from inflation, and then you can just use ordinary classical perturbation theory to figure out how it's going to grow under the influence of gravity. And a second point, well, so I mentioned cosmological perturbation theory. So what I showed you yesterday about the quantum fluctuations of the inflaton, so that is a kind of a hand-wavy approach, and it was realized early on by Sasaki and then later Mukhanov that to do it rigorously, you really need to perturb the metric too. And the scalar fluctuations do not get quantized independently of the metric fluctuations, but you have to find a linear combination of those that's the real canonically normalized field variable. And so this is the rigorous approach. Fortunately, it gives the same answer as the less rigorous approach I showed you. Another thing I wanted to mention was that the sorts of perturbations we have been talking about, the standard ones from single field inflation, are known as adiabatic perturbations. And it means that you can think of them as being really perturbations in the temperature, and they lead to perturbations in the density, which for radiation, since radiation is t to the fourth, that would just be 4 times delta t over t for radiation. And since matter, like baryons or dark matter, goes like mass t cubed, it would be 3 times delta t over t for matter. And so it means that all species of radiation and matter are related to each other by this proportionality. So that's known as an adiabatic perturbation. But another possible fluctuation is ones where you don't let the density vary, but you just rearrange the relative densities of different species. So for instance, I could rearrange the amount of radiation and matter in the fluctuation such that delta n over n is 0, but I have relatively more radiation than matter. And that other kind is known as an entropy or an isocurvature perturbation. And I didn't talk about those because they're predicted to be 0 in the simplest models of single field inflation. But if you have if you have multi-field inflation where several inflaton fields are playing a role, then it's a generic prediction that you will get these kind of perturbations. And you don't want them to be prevalent because it turns out that they give a very different prediction for the CMB, the Doppler peaks, relative to, so the adiabatic ones, this is what we see. And if we had pure isocurvature modes of various kinds in the cold dark matter or neutrinos or I forget what the other one is, but you see that you get very different predictions. And so it means that the relative contribution of isocurvature perturbations is limited to be less than something like, so it has to be less than 7% of the total contribution to the density, to the fluctuations. An exception, you could have a situation where these are very prevalent early on, but could decay. So if you do this with a particle that decays, it can decay in such a way as to turn into an adiabatic perturbation. And there's an interesting mechanism called the curvaton mechanism, which allows that to be the primary source of the density perturbations. And in that way, you could liberate your inflation model from the direct constraints that we were talking about yesterday and get it in this alternative way, which was due to Leith and Wands. And of course, all the references are in my notes. I also wanted to just mention non-Gaussianity. So the fact that single field inflation predicts that these kinds of, so RK1, RK2, RK3, these are equal to 0 because single field inflation predicts that the fluctuations are a Gaussian random distribution. Well, I should say almost equal to 0 because this does arise at some level from higher powers of derivatives of the inflaton potential, but these are very small in slow roll inflation. It also arises because of the nonlinearity of gravity, but that's also very small. And so these contributions are much smaller than what's currently measurable. And well, now Planck just gets upper limits on the level of non-Gaussianity such that it's just not interesting from the point of view of single field inflation. And you have to build more complicated models of inflation in order to get non-Gaussianity at an observable level. But since there's no hint of it in the data yet, there's relatively little motivation to do that. I also wanted to mention, so we've only talked in terms of reheating about this very simple model of inflaton decay, perturbative decay. But there's been a lot of work on more efficient mechanisms known as preheating, and that is where if you have the inflaton coupled to other fields, then by non-perturbative solution of the coupled field equations, you can find that the particles that it's coupled to can be produced much more efficiently than just through the perturbative decays. So this is a non-perturbative mechanism that leads to, it can lead to very efficient reheating. The final thing I wanted to mention is that the same trick that was able to turn the Higgs field into a suitable inflaton candidate, that is the non-minimal coupling, that can rescue other models of inflation like, so we saw yesterday that chaotic inflation is disfavored generally by data, but if you just add this extra coupling to the Ricci scalar, then for suitable values of this parameter, then you can flatten out the potential just like it for Higgs inflation, at the price, of course, of adding one extra parameter. Oh, and finally, in my notes, I show what's the precise trick for introducing an auxiliary scalar to turn R-squared gravity into something that looks like just a single field inflation model. So you can see that there. And it also actually has the answer to the question that was asked yesterday, which was, I think, what was the, in Starobinsky's inflation model, what was the significance of this scale m? And the answer is that when you convert this to scalar field inflation, you find that the coefficient of the potential is going like m squared, m Planck squared. So the significance is that the energy scale of inflation is the geometric mean of the Planck mass and that scale. And so what I said was right. That scale has to be some orders of magnitude below the Planck scale. Okay, so I would like today to move on to topic number 2, and so that's baryogenesis. And we already said a few things. The question came up yesterday as to how low could the reheating temperature of the universe be, and so I said I think that. Oops, I think I lost this. We lost this. So I made an argument that I think it should be at least 100 GeV so that we could get baryogenesis. And so I'd like to tell you, tell you why 100 GeV. That probably won't come until to next lecture. We also heard from Patty Fox when he introduced BBN, what the value of the baryon asymmetry is. Well, let me take one step back. So if you go back to the very early universe, the most natural initial condition is to have equal numbers of particles and antiparticles. And of course, if some imbalance existed before inflation, it would have gotten wiped out during inflation. There are some efforts to try and get a baryon asymmetry during reheating. So it could happen right at the end of inflation, but that's a rather special situation. And so most of the mechanisms that people think about are ones that are happening well after inflation ended. So you need some mechanism to create this imbalance. And so I believe Patty showed you the numbers that the density of baryons minus antibaryons over photons, this is the eta parameter. So that's in a range 5.8 to 6.6 times 10 to the minus 10, which one can determine from BBN. But now with the CMB, which is also quite sensitive to this number, we get a better precision, which is compatible with this range from the CMB. Another way that's often convenient to express this is in terms of baryons over entropy. And so if you just compare the current entropy density of the universe to the photons, that's smaller by a factor of about 7. And of course, this is a convenient way to parameterize things because if you know the value today, then it's going to change not very much as you go back in the early universe to the extent that entropy is conserved. So if we know the value now, then we know what target we're looking for at the moment when we want to create it. So you've probably heard of Sakharov's laws, and Sakharov was quite prescient because in 1967 he pretty much enunciated what you needed. It wasn't laid out quite as clearly as we state them today, but all the elements were there. And so what you need to make a baryon asymmetry, well, you need baryon number violation. That's pretty obvious. If you're starting from no baryons, you need to violate baryon number. You also need departure from thermal equilibrium. And the one that's less, well, we'll argue why, why it's more or less obvious. And you also need CP, actually CP and P violation. So I'd like to go through those, and starting with baryon violation, because this is one element that's present within the standard model to a sufficient extent for baryogenesis. And so it's nice not to have to invoke more new physics than you need to in order to explain this. And so in the standard model, baryon number is violated by the triangle anomaly. So if I use this cross to denote the current let me use it to denote the divergence of the current for baryon number. And if I couple this to weak gauge bosons, then the anomaly is that this is equal to minus G SU2 squared over 64 pi squared epsilon mu nu rho sigma, and the weak gauge boson field strengths contracted with epsilon tensor. And that was found by Tuft in 1976. So it says that if you're in a background where the W boson field strength's non-vanishing, then baryon number is not conserved. And what is this baryon current explicitly? Since baryon number of quarks is 1/3, it's 1/3 the sum over all quark flavors of Q bar F gamma mu QF, just the Dirac current of the quarks. Now there's a long story about how precisely baryon number gets violated in the standard model, and it has to do with the non-trivial vacuum structure of SUN gauge theories. So we don't have time for that whole story, but one can illustrate the vacua of SU2 or SU3 gauge theory as having some kind of potential energy as a function of a topological number called Chern-Simons number. If you don't know it, don't worry about what it is. The important point is that we have these degenerate vacua, and it's possible to tunnel between them. And it turns out that every time you have one of these tunneling events, then baryon number is violated, and lepton number is violated. And it's violated, you can picture it as being due to something called a sphaleron, which is, it's a field configuration that consists of non-vanishing W bosons and Higgs field, which sits right at the top of one of these barriers. So you have to pass through that configuration in order to tunnel. And you can, it's a non-perturbative configuration, but you can picture it as being like a Feynman diagram, except I didn't want to draw so many here. And every time you have a sphaleron interaction, you create or destroy 9 left-handed quarks and 3 left-handed leptons, 1 from each generation. So you choose one element of the doublet from each generation in such a way that charge is conserved. And so this has the property that baryon number and lepton number changes by 3 units, the number of generations, every time you have one of these events. Now, as Tufts showed, this process is negligible at vanishing temperature, and the way one can do it is to find an instanton which interpolates between these two vacua and compute its action. And that instanton action, which governs the tunneling probability, it turns out to be 8 pi squared over g2 squared. So that's about 187. And so the rate of these baryon violating processes, the rate per unit volume, goes as a typical scale for the weak interaction. So the weak scale to the 4th times e to the minus s. So you see it's extremely suppressed. And I'll just raise this a little bit for you. And if we want to know how many of these events happened in the whole visible universe since the beginning of the universe, not accounting for the effects of finite temperature, then we would, sorry, this is, to be explicit, let me write this as gamma per unit volume. Then the number of events would be the Hubble length to the 4th, gamma over v. And if you plug in the numbers, you find 10 to the minus 25 decays. So this baryon violation in the standard model is completely irrelevant at 0 temperature. But something more interesting happens when we go to high temperature. At high temperatures, it melts these barriers. These barriers depend on the VEV of the Higgs field. And the Higgs field, the electroweak symmetry is restored at high temperatures. So these barriers just go away. And then nothing is suppressing you from making these transitions except for, you have to make a field configuration that has the right topological properties. S is the action of the instanton. Yes?
Is that H naught or is H evaluated at the time when this happens?
I'm talking about today. So this is today. So I'm saying H naught to the minus 3, that's the size of the visible universe. H naught to the minus 1 is the age of the present universe. So I'm just saying, if we ignore finite temperature effects, that's what we would see. Yeah?
At high temperatures, the SUN, theta structure of the SUN, is it still exist in the high temperatures also?
Well, the existence, well, you could say that now everything becomes degenerate, but it's still possible to have these transitions that violate baryon number. And you pass through field configurations which are like sphelerons in that they have the same topological charge as the conventional speleron, but now they're much more, say, fuzzy. They don't have such a definite structure.
But in the normal vacuum temperatures also, we have the theta structure, right, for the SU3. That gives the anomaly.
So you're talking about QCD,
Yes.
theta vacua? Yeah, so same thing happens for QCD. The potential, that potential goes away and the mass of the axion goes away as a power of the temperature.
Maybe this is just a matter of nomenclature, but I thought the 0 temperature effect is an instanton effect.
That's what I said. Yeah, that's exactly right. So this is the action of the instanton. But I just mentioned the spheleron as being, so spheleron is like the t equals 0 cross section of the instanton. It's something you have to pass through when you have an instanton transition. But then if you do a high temperature calculation, before this at temperatures where this still exists, then that precise Faleron becomes an important part of the calculation. But we don't really care about it for our purposes. So at high temperature, above the electroweak phase transition, then this rate per unit volume is only suppressed by the weak coupling constant. And numerically, it turns out to be, so it's been determined by lattice calculations by Guy Moore and collaborators quite precisely. So it's very close to 1 times 10 to the minus 6 temperature to the 4th. And now if you want to ask, when did these Faleron interactions come into equilibrium in the universe? Well, you have to decide what's a relevant volume. And so the most natural volume to consider is if you take V to be 1 over T cubed, so a thermal volume where you have approximately 1 particle of each species in the plasma, then you find that this rate, then you find that, so gamma is then proportional to some number times T, which is a smaller power than the Hubble constant. And so you see that at very high temperatures, Falerons were out of equilibrium. They come into equilibrium at some temperature around 10 to the 13 GeV. And that will be relevant to our discussion about leptogenesis. Okay, so that's a source of baryon violation in the standard model. I'll just mention a few other possibilities. And one of the first ones to be considered was going back to grand unified theories. And that was really the first model of baryogenesis worked out by Nanopoulos and Weinberg in 1979. And people really figured out a lot of things around that time. So in the SU5 grand unified theory, you have these gauge bosons that couple to leptons and baryons in a way that violates baryon number. So you have one set of gauge bosons called X, and they have couplings to leptons and quarks, or quarks and quarks. Notice this is conjugate, so this is like quark and quark, not QQ bar. And also other interactions between quarks and leptons. And if you just try to assign baryon and lepton number to these X bosons, you see there's no way to do it consistently. And in fact, I also want to mention there's another set of gauge bosons that have fewer couplings. I want to mention it because I'm going to use them for an example. So there's one called X prime, and it only has 2 kinds of couplings, but still, you can see there's no way I can assign, if I tried to say, okay, the baryon number of X prime is minus 2/3 to cancel this, then it doesn't work for this interaction. And we'll come back to this example. Another example is in supersymmetry where R parity is violated. And one of the superpotential terms you could write down in that theory, it's the one that people call lambda double prime, is one involving the superfields of the right-handed superfields of the up, down, and down quarks. And so to turn that into a potential parameter, I can replace any one of these fields by its corresponding squark and the other two by the quarks. And, but they all carry the obvious baryon number. Well, people normally like to forbid these things to prevent proton decay. But if that's the only R parity violating operator you write down, if you don't write down the ones that violate lepton number, then you see there's nothing for the proton to decay into in this theory. So that would still be allowed. Okay, so those are just some examples of baryon violation. And now I'd like to turn to the next Sakharov criterion, which is loss of thermal equilibrium. And the way to see that you need that is that if you had some process that would produce a baryon asymmetry, but it was in thermal equilibrium, then the inverse process would just undo whatever your process did. And by definition, in thermal equilibrium, the rates of those two processes are the same. So no net change can take place unless you have loss of thermal equilibrium. And instead of trying to prove that in a general way, I think it's instructive to just do an example. So I'm going to go back to the gut theory and talk about the example of out of equilibrium decay of a heavy gut gauge boson, and I'll take it to be the X prime, since it's simpler, has simpler couplings. So out of equilibrium decay, it means that the decay rate is smaller than the Hubble rate, and so these particles are going to be hanging around at low temperatures. Actually, we want them hanging around at temperatures below their mass. But no, I guess gamma over h is sufficient. Anyway, so the way this is going to work is that we want to have X prime, and of course it's antiparticle. Notice it's not a self-conjugate particle. If you look at these couplings, it has electric charge. So X prime and its antiparticle are both going to be decaying into these particles, and we would like to see how that can happen such that a net imbalance of baryons and leptons is created. And well, already I have to invoke CP violation to do that, because if the particles and the antiparticles both decay in exactly the same way, then it's clear that their decay products are going to just be equal numbers of particles and antiparticles. So we have to have an asymmetry in the decays. So let me just define that CP asymmetry, even though we're going to come back after this to talk in more detail about how you get this. So the CP asymmetry in the decays is defined to be the net number of baryons that we're going to get from the decays of these guys, assuming that we had equal numbers of them to begin with. So I'll weight all of these decay rates by the baryon number of the decay product. We have X prime decaying into a lepton and an up quark from the first interaction. And so that creates baryon number 1/3. And from the second interaction, we're going to get minus 2/3 because that's an X prime going into an anti-quark, two antiquarks, Q bar, D bar. So that's the contribution from the X primes. And then we have to subtract the corresponding contributions from the antiparticles, because they come with the opposite baryon number. Okay, so that's the rate at which we're going to produce baryon number. And to get a dimensionless quantity, let's divide this by the total rate. So of gamma X prime going to anything, and its antiparticle. So that tells us the net number of baryons that we're going to get from the decay of an X prime or its antiparticle. Now the next thing we'd like to do is to write down a Boltzmann equation for that. So let me go over here. So the Boltzmann equation will take the form, and we want to write an equation describing the change in the baryon density. And as always happens, there's a dilution term from the fact that NB is going down just due to the expansion of space. On the other side, we have the collision term of the Boltzmann equation. In this case, it's decays and inverse decays. So each decay will give us epsilon number of baryons, and we have to weight that by the density of X prime and the density of X bar prime and the rate, the total rate of these things to decay. And CPT theorem tells us that X prime and its antiparticle decay with the same rate. So I don't have to write anything concerning gamma of X bar prime. Okay, that's the contribution from the decays. So I'll just denote it by this diagram. But of course, anything that could happen in one direction can happen in the other direction in the early universe. So we have to subtract that. And that's why this has to be out of equilibrium. These two things will exactly cancel each other if it's in equilibrium. But the way they do that at first looks kind of mysterious. So let me write this as a sum over all possible final states, y and z, and also over initial states, so X prime or its antiparticle. And I'll write the baryon number of the final state as by plus z. And then the probability of this happening will be proportional to each of the individual densities of those particles. And then we'll have a cross section. So this will be the cross section for producing a single gauge boson. So it's sigma y plus z goes to x or x bar times the relative velocity. And you look at that and you think, gee, these look so different from each other. How could they conspire to cancel just by being in thermal equilibrium? And to see that, it's instructive to go back to the fundamental formulation for the collision term. So the full collision term that includes both of those things. And I'll just write a little abbreviation for the Lorentz invariant phase space of each particle. I'll call it d pi. I think that's also what Kolb and Turner use. So that's d3p over 2 pi cubed square root of 2e. And then this collision term can be written as a product of over all the particles, initial or final. And then we have to integrate over all of their phase spaces. And now we have to write down the distribution functions. So let me call this particle 1. I'll call these particles 1, 2, and 3 here. So this term is proportional to the distribution function for particle 1. But we also get Fermi-Dirac suppression factors for the final states. So that's 1 minus F1, 1 minus F3. Those are the things that Patty told you we can ignore in the early universe. But we'll see in the case where we want to see how equilibrium makes this vanish, we can't ignore them. And then similarly, for the inverse decays, we have to subtract and we multiply F2, F3, and for this final state, we actually, it's a boson in this case, so we get a Bose enhancement factor 1 plus F1.
Previous term is not 1 minus F.
Oh, sorry. Yeah. And now you can do a little algebra, and you can show that that 1 minus F is equal to e to the beta e times F for the Fermi-Dirac functions. And you can show that 1 plus F is equal to e to the beta e for the Bose-Einstein functions. And when you do that, then you get a bunch of cancellations in the square brackets. And you find that this thing in the square brackets can be written as F1, F2, F3, e to the beta E2 plus E3 minus e to the beta E1. And now you see that by energy conservation, this just vanishes. And so that argument makes it look like, well, this thing should always vanish. But of course, there was an implicit assumption here. I assumed equilibrium distributions. This is a special property of the exact Fermi-Dirac and Bose-Einstein equilibrium distributions. But what we want for this situation is that the decaying particle will be far out of equilibrium. So we need for F1 to not be the equilibrium Fermi-Dirac distribution. For the purposes of our Boltzmann equation, of course, we're more interested in the form of the number density rather than the phase space density. And so let's see what that says in terms of the number density. So generically, the number density for our decaying boson is this integral. And if we go to the low temperature limit, where the temperature is much less than the mass, then you know it's this exponentially, this Boltzmann suppressed distribution. But we want a particle that's decaying, that's hanging around for much longer than t equals m, because it's got such a slowed decay rate. And so, of course, what would enforce this? It's if the interactions of the particles were strong enough to keep it in thermal equilibrium. So we are assuming that that's not the case. And therefore, instead, what we expect for such a particle is that its density is just equal to what it would have been for a relativistic particle. So before it started getting Boltzmann suppressed, the density of a relativistic boson would have been this, and now we're just saying this is now getting diluted only by the decays. So that's the correct approximate expression for a particle out of equilibrium. And of course, for small decay rates, this is much bigger than this, and therefore therefore the decay term is much bigger than the inverse decay term, and as a zeroth approximation, we could just ignore this term. So suppose we make that approximation, then the Boltzmann equation becomes easy to integrate. But as Patty was, yes? I'm saying that, so this term, let's see. Yeah, so I'm saying we know that this term is equal to this term when things are in equilibrium. And I just showed you what the first term looks like when it's in equilibrium. So that means the second term has this form. And now I want to go to the situation where the first term does not have that form, but the second term still does, in order for that thing to vanish if the particle was in equilibrium. So the first term is like this, the second term is like this, and I'm just assuming that gamma is such that this is much bigger than that.
So you said you need F1 to be not a equilibrium Fermi-Dirac distribution?
Bose-Einstein. Bose-Einstein, thank you. So as Patty showed us, the convenient way to frame the Boltzmann equation is not in terms of the number densities, but in terms of the abundance. And that's also the thing that we want to compare for the Baryogenesis symmetry as we parametrized it, where S is the entropy, total entropy density. And so if you just divide both sides by S, well, one thing that's nice is that gets rid of the Hubble damping, the 3H, because this ratio now is not diluted by the expansion. So the Boltzmann equation simplifies to yb dot is approximately 2y x prime. So that's the abundance that of the x prime particles. And we just get e to the minus gamma t gamma epsilon. And so now you can just integrate this, and you find that the final Baryogenesis symmetry is just equal to 2 epsilon times the initial value of the x prime. And since the x prime initially was in thermal equilibrium, it's going to have an abundance which is just of order 1 over the total number of particles. So you can estimate this as being 1 over G star S for the entropy. Okay, so that's something like 1 over 100, or maybe 1 over a few hundred in the gut model. And so that's telling us we need, how big epsilon do we need? Something of order 10 to the minus 8 in order to get the observed baryon asymmetry.
Since k is negative in that exponent, shouldn't you have a sign flip with 3?
Let's see. Are you saying this should be minus?
I think so. Not sure what
But
it is.
okay, I'll have to. Well, I'm not sure. I have to check, but it doesn't matter too much because we don't know. I mean, the overall sign of the baryon asymmetry, that's just a convention. If it was negative, then we would just rename the proton as the antiproton. Yeah.
I'm a little confused over here. You say that out of equilibrium you need the number density to be called like the temperature cubic. Whose temperature? If you're not in thermal equilibrium, then it makes no sense to talk about the temperature of the baryons, right?
That temperature is just the temperature of the thermal bath.
Okay, so is there another coefficient, or is it another numerical coefficient, or is it exactly that? I mean, it seems funny that a fluid that is not in thermal equilibrium depends on the temperature of another bath that is not called thermal.
Yeah, so
Yeah, that's right.
yeah, so the T is just keeping track of how it's getting diluted by the expansion. And then, so if it was a totally non-interacting particle, then it would not be Boltzmann suppressed because it would just have some abundance that's the same as that of radiation, and it would just keep falling like that to arbitrarily low temperature. So the only other source of time dependence would be due to its decays in that totally decoupled limit.
Would it be appropriate to say that it's still in kinetic equilibrium, but not, but there's no more number-changing processes at this point?
Yeah, I guess you could say that.
Well, if that were the case, you would have a temperature and a chemical potential, but you would still have a Bose-Einstein. I mean, you're out of kinetic equilibrium, right?
But for these purposes, I don't really care about that question at all. I just care about the number density of the particles. And I mean, so I'm only relying on the fact that its number density. So if it didn't decay, then its number density would just remain constant. Its abundance would remain constant. So the only thing that's changing that is its decays. And those details are, I mean, maybe you can quibble with those details. All I care about is this equation.
Why is there no T in that equation, though? Where did temperature dependence go when you went from N to Y?
Why is there
You
no?
go from N to your abundance.
It gets canceled out. So when you divide by S,
Oh, right.
that cancels out the T cubed. That's why this is such a convenient variable for the Boltzmann equation. Now, oh, and incidentally, this is totally, you didn't need the Boltzmann equation to come to this conclusion, right? Because it's just saying that every particle or antiparticle will, on average, decay into epsilon baryons. Okay, so this is totally brainless, intuitive result. But it's also a crude approximation because you would like to take into account the effect of the other term in the equation. So if you wanted to do that, then you can still do it. It just becomes less trivial integral. But well, we can do it here actually. So if I don't want to make this approximation, then I can write down the full, I can write down the full thing. So it would be 2 epsilon gamma y x prime of t. And then I know that the thing I'm subtracting has to exactly cancel this if this is in equilibrium. So that's the great power of this argument, because we know now a relatively simple expression that we can write to take this inverse decay into account. And that just involves the equilibrium number density of the particles. And this equilibrium abundance, you can approximate it as simply being, well, 1 over g star when the temperature is much greater, and m over t to the 3/2 e to the minus m over t over g star when t is less than m. So now I could just put that back into the equation and integrate. It's also convenient, as Patty, I believe, already showed you, to change the time variable for x. So let x equal m over t, and then change the time variable for dy dx equals whatever you need to do that change of variables. I'll just show you the final result because I'm leaving it for you as an exercise if you want to work it out yourself, that the final baryon asymmetry, when you include this washout, takes the form epsilon, the initial value of y chi prime like we had before, and we get gamma divided by the Hubble constant evaluated at temperature equal to the mass of the decaying particle. And then we get whatever we needed to cancel out those terms to agree with our previous estimate, minus a number which is of order 1. And the nice thing about this result is it shows you that what parametrically do you need in order to satisfy this out of equilibrium requirement. So it does, according to this, it does depend on the ratio of Hubble parameter to decay rate. You want that to be much bigger than order 1. Yes?
Why is the Hubble parameter a function of mass?
So what I mean by h of m, h of m is equal to h evaluated when the temperature is equal to the mass. And this expression also appears frequently when you solve the Boltzmann equation for freeze out of dark matter. And, well, if you do this very carefully and don't just make some rough approximations like I did here, then you should find that this whole thing goes to 0 in the opposite limit where gamma is becoming much bigger than h. All right, so that's the out of equilibrium requirement illustrated. And finally, I want to talk about CP and P violation. Sorry, it's not CP and P, it's CP and C. So please correct what I said before. You don't care about parity violation, you care about the difference between particles and antiparticles, of course. And you need both, because if either one was not present, then that would force this epsilon asymmetry to be 0. So let me just remind you, what is the action of these symmetries, transformations on a Dirac particle? Under P, a Dirac particle, which I write in the chiral basis, as you would expect, left and right components get traded for each other, and the x dependence gets reversed. For C, so that turns out that we get psi going to minus sigma 2 psi right star and plus sigma 2 psi left star. And then for CP, you just combine those and you get psi going to minus sigma 2 psi left star and sigma 2 psi right star. That's acting on a Dirac fermion, whereas for the boson, the gauge boson, then parity just reverses the sign of the spatial components. Charge conjugation, it introduces an overall minus sign and complex conjugation, and then CP, of course, combines those. So the relevance of this for the example that we were talking about is how does it affect the couplings that lead to the decay? And how can we see this epsilon asymmetry coming about? And so if we write those couplings out, we have some coupling constant. I'm going to write, actually, instead of the particular model that we were considering, I'm going to consider just a more toy model. Let's let X decay into some particles, psi and chi bar, which I'm going to consider to be left-handed. So I want to consider a toy model. It's a little simplified from the actual gut model, where we have interactions of a left-handed fermion psi bar left and a gauge boson x mu gamma mu, and another fermion left-handed chi left. Then we will have its Hermitian conjugate interaction. Now, if you apply those CP transformation properties, you find that this transforms into lambda chi bar left x dagger dot gamma psi left plus lambda star psi bar left x dot gamma chi left. That's under sorry about that. If you compare these two things, then you see that these would be equal to each other if the lambda coupling was real. So we need lambda not equal to lambda star to get CP violation. And so that's a generic requirement for CP violation. You want some complex coupling in the theory. And of course, that's exactly how it happens in the standard model. It's the couplings of the W boson to quarks which have a CP violating phase. However, if you just look at the decay rate for X goes to, so let's pick out one of these channels, and we have X decaying into psi chi bar. There's just one channel. And we have X bar decaying into psi bar chi. You see that we can't get any asymmetry here at tree level because these are both just going as the square of lambda. So even though it's a necessary requirement to have a complex coupling, we see that it's not sufficient. We need to do more. And what this is telling us is that the phase that's present in this coupling is not physically relevant. In fact, it can be removed by a field redefinition. So suppose lambda is equal to modulus lambda e to the I theta. And then you can see by looking at our interaction that if we just do a field redefinition on the X boson, which we can because it's clearly a charged field here. It's coupling to different fermions like the W boson does. We see that this just removes the phase from the interaction. And the general statement is that if you want to see a physical effect of CP violation, you have to avoid this somehow. And generally what that means is that you need several phases and several interactions such that you don't have enough freedom to remove all of the phases by doing field redefinitions. So let me show you an example. Or how do we fix up this theory in order to avoid that problem? We need to introduce several couplings and several interactions. So I'll introduce lambda 1 coupling to coupling X to psi bar and chi. And I'll introduce lambda 2, which couples X dagger to psi bar chi. So then you see, we better not think of this as being, of these things as being electrically charged, or that wouldn't be allowed. But in our general toy model scenario, there's nothing forbidding that. But that's not enough. It turns out we need to introduce another field, some complex. Actually, it doesn't have to be complex. Some scalar coupling to psi bar left and psi bar left conjugate, and another coupling, similarly coupling this scalar to chi bar left and chi left conjugate. And you'll see why did I cook up something like that before? Yes?
Is that second term supposed to be chi bar left? No, not that. Chi bar left and psi left.
No, I think it's as I wrote it. So the only thing I changed here was X goes to X star. And the reason I wrote this down is because the way you always get this epsilon asymmetry in out of equilibrium decays is by considering not only the tree level diagram, but a loop contribution. So if we want to know the decay into psi and chi bar, then of X, say, then we have the tree diagram. But with the interactions that I wrote down, we can also write a one loop contribution. So we have X, and now we can take the complex conjugate, the Hermitian conjugate of this interaction, and write lambda 2 star. And then in the loop, we will have psi bar chi, which is the opposite of those final states. And But because of these new interactions that I wrote down, I can turn psi bar into a psi by exchange of scalar field. So there's a G1 star, and there's a G2. There's that diagram. There's also a diagram which is a self-energy diagram of the X particle. But let me just focus on this diagram, even though both have a similar function. Okay, so this is the one loop corrected matrix element for X decaying into psi and chi bar. And now the CP asymmetry is going to be defined to be that matrix element squared minus the one for the CP conjugate process, X bar goes to psi bar chi squared, divided by the same thing with plus sign in the middle. And now one can show that this no longer vanishes. And the reason it doesn't vanish is because the loop diagram introduces an additional imaginary contribution to the equation. And this is coming from unitarity of the S matrix. And so what, yes?
You have lambda 2 is staggered in that second diagram, but not in the second term?
We have the Hermitian conjugate of
Yeah, so I needed to Hermitian conjugate. So I have this, all of this stuff plus Hermitian conjugate.
Okay.
And I'm using the Hermitian conjugate to get that interaction.
Okay.
And so there's a general general theorem, unitarity, that tells you when you can get an imaginary part of the amplitude coming from that loop. And this is the optical theorem. It's 2 times the imaginary part of X decaying into psi chi bar will be equal to the sum over the spins of psi bar and chi in this example. And we have to integrate over the phase space of... so what we're doing is we're putting the intermediate psi and chi in that loop on shell, if they can go on shell. If they can't, then this is going to vanish. And then we multiply by the matrix element for X decay to psi bar chi times the matrix element of, in this case, so it's the matrix element for this process times the matrix element for this process. We're cutting the diagram, putting those particles on shell, and we have the product of those matrix elements appearing. And so one can encode this statement from unitarity in a nice rule due to Kutkowski, which says in order to find this imaginary part of the amplitude, just replace any internal propagator that can go on shell. Actually, I have a picture here, don't I? Yeah, so here's a picture illustrating this Kutkowski procedure. You imagine cutting the diagram and extracting the imaginary part of the loop by taking any propagator that's on its mass shell, or that's being cut, and replacing it by something that puts it on its mass shell with positive energy. And so let me just show you how this gives us a non-vanishing epsilon schematically. So suppose that when we calculate this loop diagram, we find that the matrix element for x decaying into psi and chi bar is equal to the tree level contribution from lambda 1. I'm not going to write all the Dirac spinors. I'll just write the couplings. And then we see the loop goes like lambda 2 star, G1 star, G2 times some number that we get from doing the loop diagram, which will have a real part and an imaginary part. And we see that for the inverse process, x bar goes to psi bar chi. Well, that will be lambda 1 star. And, well, we'll take complex conjugate of everything except this phase that's coming from the loop. It doesn't get complex conjugated when we consider the other process because it's just a kinematical effect. It's the same loop diagram in both processes kinematically. And it's that mismatch between this being plus I in both expressions and everything else being complex conjugated that gives us a non-vanishing result when we compute the CP asymmetry. And so if you just take that expression and plug in to our expression for epsilon, what you get is 2 times IB lambda 1, lambda 2, G1, G2 star, minus its complex conjugate, divided by, for the bottom, we can ignore those small loop contributions and just keep the tree level. And so you see that this is equal to minus 2b over lambda 1 squared. And we get the imaginary part of lambda 1, lambda 2, G1, G2 star. So by doing this exercise, what we've found out is that there is an unremovable phase. If we take all of these to be complex in general quantities and we form that product, then it must be that no matter what field redefinitions we do, we can never change this phase because that's something physical depends upon it. And so that's showing you why I had to add all of these things. If any one of them vanished, then I would get nothing. And so you can go back and you can just try to do field redefinitions and convince yourself that this is an unremovable phase if you want to.
Could you explain again why the I doesn't get conjugated? Why the I term doesn't get conjugated?
Yeah, it's because, so when you write down this loop diagram, this A and this IB is just what you get from writing the propagators and replacing all the couplings by just 1. And that expression doesn't care whether these are particles or antiparticles. These are just Dirac and boson propagators in the loop. And so it's just some number.
Does the statement that the phase is irremovable depend on phi being a real scalar, or can it be complex?
Let's see. I think it doesn't matter whether, well, that statement must not depend on it because what I derived there is the correct result. So, yeah, I think it cannot matter. Okay, I guess we can stop for coffee then.